In this lecture we will discuss the so called fundamental forces of nature, the forces which are responsible for all the phenomena that we see in the universe. Now you would have come across in elementary science with various different kinds of forces. You would certainly have heard of frictional force which enables us to walk. You would have heard of a force which is centripetal force, which is inward force for a particle or an object which is in circular motion. You would have heard of mechanical forces, electrical forces, magnetic forces and so on. Now all these forces, a large variety of these forces turns out can all be brought into the broad under the broad umbrella of just 4 fundamental forces of nature. In fact, the actual number that we come across in daily life is even smaller. It is generally just 1 or 2, as I will explain as we go along. But what physics has been able to do is, over the years, it has been able to identify 4 fundamental forces in nature which are responsible for all the phenomena that we see around us. And let me list those forces and after that explain one by one what these 4 forces actually imply and what their effects are. The first of these forces is the gravitational force. And in the most elementary instance, this force has been known to human beings ever since they were on this planet, because it is the force which operates here when you throw an object, when you fall down, you climb down from a tree and so on and so forth. So the gravitational force was first mathematically, quantitatively and precisely stated by Newton's universal law of gravitation, which says that if you have 2 masses m1 and m2, the gravitational force between them, F gravitational, is equal to the product of the masses divided by the square of the distance between them multiplied by a universal gravitational constant g. Okay. And this g is approximately equal to 6 times 6 point something or the other, 6.7 maybe, times 10 to the power minus 11 newtons meter squared over kilogram squared. Because I did bring these 2 downstairs and take this up here, and the physical dimensions, the units are Newton meter squared over kilogram squared, and these standard international units, capital G is of orders 10 to the minus 11. Okay. So this is Newton's famous inverse square law of gravitation. It is also implied by this law that when the 2 objects, the 2 masses are separated by an arbitrarily large distance, no matter how large r is, there is still a force between them. So even if these 2 objects were many millions of light years apart, there is still a force between them, which of course decreases very rapidly because it goes like 1 over r squared. Now I am able to say how fast it decreases like 1 over r squared, the reciprocal, the inverse square of the distance between them. So that is the first force, the gravitational force. The next force is the electromagnetic force, which is quite complicated, but in its simplest form it is almost analogous, it is exactly the analog of Newton's law of gravitation. It is Coulomb's law between 2 static charges, and that is the electrostatic force between them. The electromagnetic force manifests in many other ways as well, as we will see, but the most elementary way is when you have 2 static charges, there is a force between them which is a force either of attraction or of repulsion, unlike the case of gravity, which is again proportional to the inverse square of the distance between the charges. And this force, and let me call it electrostatic, ES for electrostatic, this between 2 charges Q1 and Q2 is again proportional to Q1 times Q2 divided by the analog of this constant, which in the units we have chosen is written as 4 pi epsilon naught and r squared. This epsilon naught is called the electric constant of the vacuum, or more popularly the permittivity of the vacuum. Epsilon naught is the permittivity and it has a certain value in the standard international units that we use. This is of the order of 9 times 10 to the minus 12 farads per meter. When we come to electromagnetism, I will explain what the unit farad means, but it is in standard international units. This quantity has these physical dimensions here. So we know its value, numerical value in certain units in these units here. Q is now measured in coulombs here, and just for reference let me point out that the Q for an electron, charge of an electron, E denoted by E, not to be confused with the base of natural logarithms. This charge here is about 1.6 times 10 to the minus 19 coulombs. So these were the two forces that have been known since ancient times in one way or another. And I might as well say right away that the gravitational force is extremely weak compared to the electrostatic force or the electromagnetic force in general in a very specific quantitative sense, which I will come and explain in a very short while. Okay. But this is known to you, it is known to all of us. For instance, if I take a bar magnet and apply it to the top of then I place a pin on the top of the table and place a bar magnet over it, the pin can be attracted to the bar magnet and it moves off the table and sticks to the bar magnet, and what this little magnet is doing is outpulling the entire gravitational force of the earth. So in that sense you can see that this enormous mass of the earth is still not able to produce a gravitational force acting on the pin which can overcome the attractive force due to the magnet on it. So in that sense electromagnetism outpulls gravity under suitable conditions, and you need a huge mass before you have a sufficiently large gravitational field which will keep it pinned down. If you did the same experiment on the surface of a neutron star, the result would be very, very different altogether. We will see quantitatively how this works here. Now these forces have been known for a long time because of this fact that they drop very slowly to 0. They are long range forces. As I said, two masses will attract each other however feebly, no matter how far apart they are. Similarly, two charges will either attract or repel each other depending on whether these two charges have opposite signs or the same sign, and no matter how far apart they are. There is one fundamental difference between these two laws. Both of them are inverse square, but we have no knowledge of any negative masses. All the masses we know of are positive, and therefore the gravitational force is always an attractive force between two like masses, like charges, in the sense that they are positive masses. In contrast, we know of the existence of both positive and negative charges, so these Q's can have either sign, and it so happens that when they have unlike signs the force is attractive, and when they have like signs the force is repulsive. Okay. On the other hand, you might say here too I can regard the masses as the analog of charges. Yes, indeed, that would be true. We have only positive masses, so they would be like charges, but instead of repelling they attract each other. This is a fundamental difference between gravity and electromagnetism, and the reason is buried in quantum field theory. We are not going to get into that now, but it is a fact of nature. This profound difference between electromagnetism and gravitation here. There is another thing that happens because of the fact that you do not have negative masses. The fact that you have both signs of charges allowed shows that forces can cancel. They can actually cancel each other. Whereas if you take gravitational masses here, gravitational force here, it is clear that this force, if you add more mass, the force is just going to increase all the time. On the other hand, there is a possibility of having a plus charge here and a minus charge here and putting a test charge in the middle in such a way that the force on it, net force on it, actually gets cancelled out. So these things are possible because of the difference in signs that is possible here, but not possible here on this side. Okay. Now what are the other two forces? Two more have been discovered, and this discovery was made in the 20th century, and these forces are called the weak force and the strong force. Okay. In stark contrast to these two forces, these forces are only observable at extremely short distances. The range of these forces is very, very short, unlike the case of these two forces where the range is actually theoretically infinite, because this r can go all the way up to infinity. The force becomes 0 only as r tends to infinity. Now what about the ranges of these forces? Let me write these down so you can see. There is no simple formula of this kind available in the case of these forces, but they are very, very important all the same. This force, the strong force, is responsible for the force between nuclei, the force that keeps an atomic nucleus stable, the force between different protons and neutrons in a nucleus, atomic nucleus, and in fact for the force that keeps a proton stable and which has quarks inside a proton, and these quarks bind together to form a proton or bind together in a different way to form a neutron. So even the constituents of the nuclei are kept in place by the strong force. Okay, so we will see in what sense this is an extremely strong force here. But the range of this force is of the order of less than or of the order of a few Fermi. So about 3 times 10 to the minus 15 meters. So a few femtometers, because as I said, it manifests itself in atomic nuclei, in the nuclei of atoms. And beyond that, this force is essentially 0, it does not exist beyond that. Similarly, the weak force is also extremely short range, and the range here is of the order of or less than or of the order of 10 to the minus 16 meters. What is it responsible for? It is responsible for radioactive decay, for fission reactions, for radioactive decay of unstable nuclei and so on. So this force here and this force here really are very closely related to each other, although they are quite distinct from each other. They both operate at subatomic scales, at nuclear scales and subnuclear scales. So that is the reason why it took so long to discover these forces, because we really needed to get atom smashers, we needed to get particle accelerators before we could probe distances short enough where these forces manifest themselves, these two fundamental forces of nature here. Now what is the other significant difference between these forces, and what is the reason why the range is very short? Again, the reason is buried in quantum field theory, which we will not get into obviously here, but the significant point about these forces is that the relative strengths compared to these two forces are very dramatic, and that is what I would like to illustrate now with a little calculation. I would like to show you how strong are these forces with some common reference point here. So let us take two protons. Here is a proton and here is another proton, and the distance between them is 1 meter. And I ask, what is the gravitational force and what is the electrostatic force between these two protons at this distance, kept at this distance? Well, this force here is of the order of this is G is 6 into 10 to the power minus 11, as I said, and then there are two protons and each proton has a mass which is of the order of 10 to the minus 27 kilograms. So this multiplied by 10 to the minus 54 divided by the distance between them, the square of the distance between them, that is 1. So this is clearly, this is equal to of the order of 10 to the minus 64, of the order of 10 to the minus 64. Okay. 55 and give another 10 for this, so you have 10 to the minus 64. This on the other hand is of the order of, the charge of a proton is 1.6 times 10 to the minus 19 coulombs. So this is 1.6 squared into 10 to the minus 38 coulomb squared divided by 4 pi, that is approximately 10, and then there is an epsilon naught which is 9 times 10 to the minus 12, so that is another 10, so 10 squared into 10 to the minus 12 out there, and then r was again 1. So this gave us 10 to the minus 10. So this thing here moves up and becomes minus 28, approximately 10 to the 28. So that is 36 orders of magnitude difference. So it tells you that the ratio of the gravitational force, or let us write the electrostatic force to the gravitational force under these conditions, namely 2 protons a meter apart from each other, is of the order of 10 to the power 38. So it shows you how much stronger electromagnetic forces are relative to the gravitational force. For the gravitational force to become significant, you need a very large mass. You need astronomical masses, and that is why gravitation controls what happens in the universe, the motion of galaxies, the behavior of galaxies, groups of galaxies and so on, or even the motion of planets. On the other hand, what happens in daily life all around us is controlled largely by electromagnetic forces, not just the electrostatic force but electromagnetic forces. A little subtlety here, you might say, where do these electromagnetic forces come from if all the atoms are neutral? The point is, slight charge imbalances are enough to cause these forces, and that is exactly what happens when you have two different signs possible. For instance, here is a famous question. Once you have two atoms, let us suppose both these are spherical atoms, hydrogen atoms in the simplest picture. So you have a spherical cloud around one hydrogen atom, another hydrogen atom here, a spherical negative charge electron cloud. So there is a plus charge here and there is 9 minus charges in a spherically symmetrical cloud. This object is electrically neutral and there is no electric field due to this object outside because it is completely spherically symmetrical. The positive charge is balanced completely by the negative charge. So is the other atom. How then would they see a random force between them, any force at all? The point is, this is not static. These are dynamic, they are moving entities, the electron cloud is not static or anything like that. So momentarily, if there is a displacement of the center of the charge, negative charge, so that you have momentarily you have a net positive charge here and a net negative charge here, this forms what is called an electric dipole. This electric dipole induces immediately a field at this point, an electric field at that point, which causes also a separation of the charge. And because you have two dipoles, it is like two bar magnets. As you know, if you have two bar magnets with north poles pointing the same direction, when you bring them closer they repel, and when you bring them in opposite directions they attract. A similar thing happens here, and there is a net force between these two objects whose distance dependence can be calculated, and turns out in this case, in the simplest picture, that the force between these two objects decreases like the like 1 over r to the power 7, and it is called a van der Waals force. So there is actually an induced electromagnetic force even if the atoms are neutral, and this is what is governing all the behavior of objects all around us. So various kinds of electromagnetic forces. Friction, for example, is ultimately due to electromagnetic forces. A lot of all of chemical binding and so on are all ultimately due to electromagnetic forces, with the added complication that quantum mechanics plays a very significant role. Things like the Pauli exclusion principle play a very significant role, but finally in the final analysis they are not strong forces, they are not weak forces, they are not gravitational forces, but they are electromagnetic forces which control the behavior of most objects around us. Okay. So these two forces in that sense are extremely crucial. Now, why is the range of these forces so small, and what are the peculiarities of these forces? That requires us to understand, it is not understandable in very elementary terms or simple terms at all, because as I said, there is no simple analog of either Newton's law of gravitation or Coulomb's law of attraction or repulsion between charges in the case of these two forces here. But the origin of these forces comes about in more or less the same way as the origin of these forces when understood at the level of quantum field theory. And today the belief today is that all fundamental forces are transmitted with the help of certain quantum fields called gauge fields, which have associated particles with it. And in the case of the electromagnetic force, the particle is the familiar photon. In the case of the weak force and the strong force, there are corresponding particles. In the case of the strong force, they are called gluons. In the case of the weak force, there are other particles called the W and the Z particles, which are responsible for mediating respectively the strong force and the weak force here. but the peculiarities of these particles, their properties will dictate what the behavior of these forces is in each case. However, these forces are responsible for a lot of physics. This force here, the strong force, as I said, when it operates within a Fermi distance of a femtometer, it is responsible for the behavior for creating particles like the proton and the neutron, nucleons. Now we know that the proton is made up of 3 quarks of a certain kind, the neutron is made up of 3 quarks of a slightly different kind, and these objects here are kept in place by the forces between the mediated by gluons, the forces between the quarks. Over and above this, there is also a little residual strong force which spills over outside the nucleon, outside the neutron and the proton, which is what makes nuclei stick together. So nuclei stick together in spite of the fact that they have neutrons which are electrically neutral and a lot of protons which will repel each other, but that repulsion is overcome by the residual strong force and the nuclei stick together. However, if you put too many protons in there and a relatively smaller number of neutrons, then it is clear that the repulsion is going to take over and finally the nucleus becomes unstable, and this is what happens in real nuclei. You might have noticed in the table of elements of nuclides that as you go up and the mass number increases, the number of neutrons becomes rather larger than the number of protons. It is not as if you have equal numbers. In the case of hydrogen, you have a single proton in the nucleus. In the case of helium-4, you have 2 protons and 2 neutrons, and so on for a while. But gradually you realize that the number of neutrons becomes larger, and this is needed, otherwise you would not have stable nuclei, because you have too strong Coulomb repulsion between the protons to make the thing unstable here. As it is, the radioactive decay of elements or even of a single neutron happens because the weak force takes over here. This force here is responsible for weak decay, and today we understand the behavior of these forces at individual levels, this and this to a very large extent, this to a rather smaller extent, although we understand the principles on which it works. The gravitational force also is independently understood at the classical level, but not quite at the level of quantum field theory. So this is still an unsolved problem. So these statements you would have heard about the unification of all these forces, that program is not complete. These two forces have been unified in a very specific sense of the word, but not yet fully unified with the strong force, and certainly not yet with the gravitational force at all. Okay. Now one could ask, is there such a unified theory at all? Does it exist? We have no knowledge of it. We think it will exist because the principles on which these forces arise, the fundamental principles, appear to be common. There appear to be some very deep common principles which tell you how these various forces arise. And there is also good evidence to believe that if you go to shorter and shorter distances, there will come a stage where these forces get unified in a very specific sense. For instance, I said, and I haven't quite mentioned this, we found the ratio of the electrostatic to the gravitational force. What about these two forces? On the same scale, what would these look like? So let us say that the strong force, if I represent its magnitude by 1, and that is for the strong force, then relative to this 1 for the strong force, the relative strength of the electromagnetic force under appropriate conditions of comparison is of the order of 10 to the minus 2. On the same scale, the weak force has a strength of about 10 to the minus 6. And the gravitational force on the same scale has a strength of about 10 to the minus 40. These are very, very rough estimates. Which sort of explains the terminology also, why this is called weak compared to the strong, and why the electromagnetic force is rather strong compared to the weak. But as you go to shorter distances, I have already mentioned that the weak force has a range of about 10 to the minus 16 meters, that is 0.1 Fermi, femtometer, whereas the strong force has a range which is of the order of a few at best a few femtometers here. If you go to smaller distances like 10 to the minus 18 meters, then it turns out that the strength of the weak force and the strength of the electromagnetic force become comparable to each other. So this suggests that as you go to higher energies, which means you go to smaller distances, or you go to the earlier part history of the universe, there would have been a stage when these forces were unified. It was the same force in some sense, and it split into two distinct forces that we see today. And that is indeed true. This is called electroweak unification, and it happens at an energy scale which is of the order of 100 times the proton mass. As you know, Einstein's special theory of relativity, and we will talk about that, has suggested to us, has informed us that mass and energy are equivalent to each other. So we could measure energy in mass units or mass in energy units in a very specific, precise sense, and on that scale, if I go to energies which are comparable to 100 times the rest mass of the proton, then the weak and electromagnetic forces tend to get unified to each other. So they were unified at some stage in the past. Okay. So much for the relative strengths of these forces. We should also write down here the ranges of these forces. The strong force, as I said, is of the order of less than or of the order of 10 to the minus 15 meters. The electromagnetic force is an infinite range force because the 1 over r squared force goes on forever for all values of r right up to infinity. The gravitational force is infinite, and the weak force is of the order of 10 to the minus 16 meters. Once again, I emphasize this short range is what made it impossible for these forces to be detected until we were able to probe what is happening inside an atom. So you need to go at least to those energies, even to nuclear energies much greater than that, in order to probe these forces here. But today we know that these are the fundamental forces of nature, and that all physical phenomena, as far as we know, can be now attributed to the operation of just these four fundamental forces of nature. So in that sense, a certain unification has been achieved. The first unification was already achieved earlier by Newton himself when he wrote down the law of gravitation. He made a very important observation, which is that the same gravitational force which caused the apple to fall, the proverbial apple to fall from the tree, also held the moon in its orbit around the earth. So he actually unified terrestrial gravitation with celestial or astronomical gravitation. So in that sense, it was the first assurance that the gravitational force is actually a universal force, operates everywhere. The next unification came when Maxwell unified electricity and magnetism, and incidentally also showed that light is a form of electromagnetic radiation. So there was the unification of electricity, magnetism, and optics and light, and that was the second great unification. The third one came much later, in the later half of the 20th century, when the weak force and the electromagnetic force were unified into one entity called the electroweak force here. And the quest is on for the unification of the strong force with these other two forces, in which case you would have what's called the grand unification, and finally that still leaves open the problem of gravitation here. Now the very difference in scales here is what makes the problem of unification extremely difficult, because you have phenomena appearing on different scales altogether, separated by a large number of orders of magnitude, and this makes it very non-trivial in order to bring these things into the same umbrella, under the same umbrella. So that's one reason why this unification program is a very non-trivial program and a difficult one, and there is no guarantee that such a theory exists as of now, although theoretically we would like to believe that it exists for aesthetic reasons of various kinds. It would also be a very unified picture. It would lend credence to many of the theoretical conjectures that have been made in nature so far. So much for the fundamental forces of nature. The take-home lesson is that the forces that we see in daily life are the gravitational force and various manifestations of the electromagnetic force. all terrestrial phenomena other than those dictated obviously by gravity in various cases of mechanical behavior and so on, all the other forces, all the chemistry and so on, they are all dictated by the electromagnetic force in its very large number of different manifestations.